So for those of you joining live, let me just say that one more time for those people that are going to be watching this. So on your front page, I have some useful links to my Zoom room, to the YouTube playlist for all my Physics 10 videos and lectures, and to the Physics 10 Canvas page. I also have a link to my YouTube channel, and then any physics videos available on the YouTube. So just to be clear, the lectures will be on Tuesdays and Thursdays on Zoom from 9:30 to about 10:45. Sometimes I might end a little bit early. You do not have to attend these live. If at all possible, I highly recommend it, but I will always post the videos to YouTube, and I will post them to your Physics 10 YouTube playlist, generally that same day. So Tuesdays and Thursdays, generally I'll have the video posted on YouTube by maybe 2 or 3 o'clock in the afternoon. Office hours specifically for Physics 10. So Mondays 3 to 4, Tuesdays 2:15 to 3, Wednesdays 2:15 to 3, Thursdays 8:45 to 9:15, and also by appointment. So if for any reason you can't attend those and you want to access me, send me an email and we can arrange a time to meet. And I also have sort of a tentative schedule of when all the quizzes and homework are due. Now, what I don't have on here is just discussions. And I'll talk about that a little bit later, but every week we're going to have just a discussion question that you're going to answer and then reply to a couple of your fellow students' posts. The homework for the entire semester is already posted. It's posted both as a Word file, which you can download if you want, or as a PDF. And these are just short answer questions that you're going to be answering once you're finished the chapter and then uploading those to Canvas. I also have practice quizzes. So for every single chapter, there is a multiple choice 10-question quiz, and it's just to help you study. So these questions will be pertaining to the chapter we're studying, and then if you click on an answer and it's wrong, it'll say, sorry, you chose the wrong answer, try again, and it'll tell you when you have the right answer. So oftentimes I will choose 1 or 2 of these questions for the quizzes or celebrations. So not only will these help you study for the quizzes, there's a good chance you might see some of them again. Physics PowerPoint slides. So these are PowerPoint slides from the publisher. So like for Newton's first law, it'll take you to just a PDF that has the PowerPoint slides that the sort of publisher gives to the instructors. This is a really nice sort of quick review of the entire chapter. I highly recommend, if you can, to read the chapter before I start lecturing on it. But if for any reason you can't, a nice thing to do would just be to go through these PowerPoint slides and it'll let you know exactly what's being covered. Under physics resources. So this was something I had a sabbatical last semester. One of the things I was working on is just getting a bunch of resources available for students. So like right now, we're going to be looking at forces in Newton's laws. If you click on that, it has some resources that'll help you. So one of the things, I have links to lecture notes that other instructors have posted online. And again, these are separated by conceptual, algebra-based, and calculus-based. So like we're studying Newton's laws. And if you wanted more information, click on Newton's laws, and it'll take you to a site that's got all sorts of information on Newton's laws, which are appropriate for conceptual physics. Other thing that's really nice is I have a bunch of these applets and animations. So a lot of these are sort of more mathematical, so they may not apply to conceptual physics, but oftentimes in class, I'll show an animation. When I do, you know that you can access them on that page. And then, so this is the big one for you, lectures and lecture notes. So again, I have a link to my Zoom room, a link to the YouTube playlist for Physics 10. And then one nice thing I have is I have your conceptual physics textbook. So this is a really nice PDF copy of the textbook. It's kind of a big file. What I recommend is just downloading it. There's a chance I'm going to probably take this link down in the next couple of weeks. So try and download this when you can. Let me just give it a second to see if it'll load. It's a pretty big file. And it's taking a while. Well, let me just come back to that. If you don't want to download the entire textbook, what I have is each chapter, I sort of just took the PDF and I extracted just each chapter. So if you go to like Newton's first law, it'll just be that chapter of the textbook. And let me just say, this is an outstanding textbook. I've been teaching physics for 20 years. I love this textbook. I use a lot of the questions in my more advanced classes. It's written in a very sort of light, sort of conversational style. It's a really, really, really good textbook. I highly recommend that you take the time to read it. A few other things. I have my lecture notes for each chapter. What I highly recommend is print out the lecture notes for each chapter. And when you're watching these lectures, what you want to do is be watching them with pen and paper in hand, taking notes as I'm going through it. Let me just say a couple words about these lecture notes. So these lecture notes, are not 100% complete. I will be adding stuff to it. These are the lecture notes that I use in class, and I've been teaching this class for a long time, so I add a lot of additional information. So what I generally have on my lecture notes is an outline of what we're going to be covering, the reading in the textbook, and then you'll see a sort of a lot of notes from me. So anything that you see in red would be like something that's for me. I'd be doing a demo or I'd be showing PowerPoint slides. So you can sort of ignore those. And then let me just scroll down for a second. You'll see things like do question 1-1. In class, I was using clickers and doing a lot of sort of peer review where I would ask a question, give students a couple minutes to talk about it, and then they would click in their answers using a clicker. We'll still do some of that, but obviously we're not going to be using clickers. So this is just warning you that stuff that you see in red was just sort of for me to remind myself to do a demonstration or to do an exercise or something like that. And then here is where I will post a link to all the individual lectures. So today is Tuesday, 1/26. When I am done with this lecture, I'll post it this afternoon, and then I'll put a link right here. So at any time you can access any of the lectures, the individual lectures. They'll also be posted on the YouTube playlist. So that is sort of your Physics 10 homepage. Let me just pause for a second and see if anybody who's watching this has any questions I can answer. Any questions from anybody who's here live? No? Okay, then I want to just touch a little bit on your Canvas page. So let's go, let me get rid of that. Canvas, nope. So many links. Okay. So the way I have sort of Canvas set up is by weeks. So every single week, there will be a new module. And in general, the way the modules are set up are, I will give you sort of an overview. The overview will tell you exactly what we're covering that week, and I'll tell you what you'll be doing. So like for this week, what you want to do is read, review all the module pages for week 0 and week 1. If you can, read chapter 2 of Conceptual Physics and my lecture notes for chapter 2. Attend the Zoom lectures on Tuesday, Thursday, and/or watch them on YouTube. And then anything that you're turning in is going to be in bold. And I'll tell you exactly when it's due. So this week, there's going to be an icebreaker discussion. Initial post is due on Thursday. Peer replies are due on Sunday. 10% of your grade is just based upon answering these discussions and replying to other students. It's just a way of promoting class participation, a way of getting students to interact with each other. The very first one is just an icebreaker discussion, and it's just about if there was a zombie apocalypse, what are 3 things that you'd want to take with you to help survive? It's just a fun little question, and partly it's because I've been watching The Walking Dead and really enjoying it. So I just thought it'd be a fun little little question to do. And then the other thing is we're going to be using something called Lockdown Browser. And it is a separate browser that's like Internet Explorer or Chrome that will only let you basically work on what's in the browser. You're not allowed to open up other browsers. You can't access other websites or anything like that. So what you're going to be doing is downloading Lockdown Browser, And then anytime you're going to take a quiz, what you're going to need to do is open up Lockdown Browser and then navigate to the Canvas Physics 10 page and then take the quiz. Let me go back, modules again. And then the other thing I do is give you one background reading is just always going to be the textbook and my lecture notes. But then I'll also show some videos that I think are excellent as sort of background information. So if you want to sort of prepare for the lecture before I start lecturing on the material, these are excellent videos to watch. And then next, can I move that for a second? No. Okay, why can't I go to next? All right, next. Zoom lectures, it's just to remind you I'm doing lectures. Let me just check the chat real quick. Love the question. I'm still having trouble downloading a Lockdown Browser. If anybody does have trouble, let me know. I have, yeah, there was an initial problem that was not being able to be downloaded on Chromebooks, but hopefully that was fixed. But I will, yeah, let me know. Send me an email and we can work that out. So I also have just links to the lecture notes and Zoom lectures and your Physics 10 homepage. I can't access the next button. Can I move this? Oh, there we go, next. So like here's your very first icebreaker discussion. It's just zombie apocalypse is coming. Who are 3 people you want on your team and why? You can take 3 items from your house to help you survive. Which 3 items do you take? So to reply to this, you just hit reply. Answer those questions by Thursday night, and then by Sunday night, read 1 or 2 of your fellow classmates' posts and then reply to a couple of them. And that's kind of it for the discussions. Homework for conceptual physics. If there's homework due that week, then there'll be some place where you can actually upload it, and I'll show you that next week. And then, so here's where you would go to download Lockdown Browser. So you click on this link. It's going to take you to this, and this is specific to Cabrillo College. So this is the link that you would use for accessing Lockdown Browser. And once after you install it, once you open it up, it'll just take you to the Cabrillo College Canvas login page. Then you would just log in like you would normally, go to Physics 10, go to this quiz page, and then take the quiz. Let me go back. And let me just show you 1 or 2 other things. So I have a week 0 orientation. This is just some information about our class, how to contact me, some tips on getting started with Canvas, and then some other useful information. So please take the time to sort of click through that, read through it, and then let me know if you have any questions. Okay, a couple of things just about how to succeed in this class. Learning online is different and it's a challenge, and you definitely have to be motivated to stay on top of everything. What I recommend is 1, print out the lecture notes for each chapter before I start lecturing, and then have a pen and paper and take notes as I am lecturing. So I'm going to try as much as possible to make this as close to a real live learning experience as I can, but obviously there are certain challenges with teaching online. And a couple other things. For Zoom lectures, you don't have to have your video on. If you feel comfortable, I would love that. It's really hard teaching to just a bunch of black boxes. And at the very least, please put a picture so you can put an avatar or something like that. Let me check chat real quick. I don't have a printer, sorry. Oh yeah, so if you don't have a printer, obviously that's okay. But if you can then just read through the notes before you attend the lecture, that would be phenomenal. Okay, let me pause. Any just general questions on the class, on Zoom, on the website, anything that I can answer before I actually jump into Physics 10 material? All right, let me Get rid of some of these links. Okay, so let me stop this share. I'm going to share a screen again and go to OneNote. Okay, can everybody see my OneNote right here? Somebody give me a thumbs up. Yes, okay, thank you. Okay, so I'm gonna start. Let's just look at what we're gonna be covering. Let me turn this on. So we're not covering chapter 2 or chapter 1. Chapter 2 is all about Newton's first law of motion, sometimes called the law of inertia. We're going to start with just a brief little historical perspective. I'm going to talk a little bit about Aristotle, Galileo, and then Newton. And then we're going to go into Newton's first law, talk about inertia in mass, Newton's first law, and net force. That's probably what I'll get to today, maybe somewhere around here. And then I will finish this chapter on Thursday. So I'm going to start with just a brief little historical perspective. So Aristotle was a brilliant, brilliant man, but a lot of what he taught is not actually correct. And one of the interesting things is a lot of his beliefs lasted for more than 2,000 years. So if you ever are thinking that physics is a little bit challenging, you don't get it right away, don't worry, we had incorrect beliefs for more than 2,000 years. So what Aristotle thought, what he believed, was that there were two kinds of motion, either natural motion or violent motion. So according to Aristotle, every object in the universe has a proper place depending upon whether it was made of earth, water, air, or fire. So right now, does anybody know about how many different elements we have? Things like carbon, oxygen, nitrogen. There's 118 known elements. You've got hydrogen, nitrogen, carbon, oxygen, and so on. What Aristotle believed was that everything made on Earth was made of one of 4 different types of elements, either earth, water, air, or fire. So our periodic table right now has 118 known elements. In Aristotle's time, if there was a periodic table, there'd be 5. 4 that on Earth, earth, water, air, and fire, and then anything in space he thought was made up of something called quintessence. And an object has sort of a natural resting place. Anything made, let me go back over here. Everything had sort of a natural resting spot. And what Aristotle considered natural motion was an object, that's horrible. I'm still getting used to this writing tablet. So natural motion was motion of objects moving towards their natural resting spot. So I'll come back to violent motion, but everything on Earth was made of either earth, water, air, or fire. And anything in space, he believed, was made up of something called quintessence. And every one of these elements, he believed, had a natural resting spot. And any object would naturally move towards its natural place. And it would remain there at rest unless something prevented it from doing that. And that something he would call violent motion. So natural motion, objects moving towards their natural places. Violent motion was motion due to contact with an outside object or agent. And what he believed was that anything made of earth or water, the natural motion was downward towards the earth. So if I dropped a, that was easy button, and it fell. The way that Aristotle would explain this was that this easy button was made up of either earth or water or some combination of it. And the natural motion of anything made of earth and water was to fall straight down towards the earth and be at rest on the earth. natural motion of anything made of air or fire was up towards the sky. So natural motion, according to Aristotle, was either straight down if something was made of earth or water, or straight up if it was made of air or fire. Now, if I threw an object straight up, that is what Aristotle would consider to be violent motion. Because if this was made of earth and water, its natural tendency would be to fall straight down towards the center, towards the earth, and remain there. But I could cause something to go against its natural motion by exerting a force on it, and he called that violent motion. So going back up here, natural motion was any object moving towards their natural place. Earth and water, the natural place is down. Fire and air, the natural place was up. And violent motion was any motion due to some object which was exerting a force on it, causing it to go against its natural tendencies. Now, what they did know was that things in space tended to move in circles. And so what he said was anything in space was made up of something called quintessence. And the natural motion of something made of quintessence was circular. So anything made of earth or water, natural motion was downward. Anything made of air or fire, the natural motion was upwards. And then anything made of quintessence, the natural motion was circular. Now, here's an interesting thing. According to Aristotle, the heavier an object was, it means it was made up of more earth or more water. And therefore, if I had something made of more earth, and anything made of earth naturally wanted to be towards the earth, then it makes sense that heavier objects would strive towards the earth more than lighter objects. So what Aristotle taught was that the heavier an object was, the faster it would fall. And what's pretty impressive about this, in sort of a bad way, is that these ideas lasted for 2,000 years. Think about that. For 2,000 years, we believed that the heavier an object was, the faster it would fall. What we're going to see is if there's no air resistance, all objects will fall at the exact same rate. And we'll see that more in next chapter, chapter 3. But for 2,000 years, we believed that, so if I have a pen and an easy button, this easy button probably weighs 50 times the mass of this pen. What Aristotle would have taught was that if I drop these two objects, the easy button would have fallen towards the earth 50 times faster. And for 2,000 years, that belief stood, which is a pretty impressive thing. Now, for 2,000 years, did nobody pick up a heavy rock and a light rock and drop them and see that they fell at the same rate or close to it because of air resistance? People probably did. Without going into too much history, you did not go against Aristotle in the church. Basically, people believed that you could figure things out just by thinking about it, and you did not need to do experiments. Well, finally, so remember, Aristotle, he's around 350 BC. So he was living, 2,400 years ago. And then about 2,000 years later, Galileo was the first person to really start to think about whether or not Aristotle was correct. So Galileo was living in the late 1500s. And what he did is he studied the motion of objects, rolling objects. And what he did is he used inclined planes to study the motion of objects. Now, why did he use inclined planes? Why didn't he just drop objects and sort of look at their motion? Well, if you think about it, in the mid 1500s, late 1500s, they didn't have accurate timing pieces like we have now. They didn't have stopwatches or things like that. So a quick little question, does anybody know what Galileo used to measure time? And the answer is he just needed something that occurred at regular intervals. So sometimes he used his own heartbeat to measure time, or you could use dripping water. So if I was trying to measure how long it took for something to fall, I would drop it and then try and measure my heart rate, you can see that that's not the most accurate way of doing it. So what he needed to do was slow down the motion of objects. So rather than dropping objects straight down and then trying to take some measurement using his pulse, what he did is he rolled objects down inclined planes. And here's what he noticed, and this makes sense. If I have an object which is rolling down a plane, well, obviously that object is going to speed up. We all know that just from normal everyday experience. If I have an object which is going up a plane, we know that the speed is going to decrease. Well, if it's going to increase going down a plane and then decrease going up a plane, it kind of makes sense that if I have a level surface, the speed is not going to change. But that is not what Aristotle taught. What he would have taught is that the ball is made of either earth or water, things made of earth or water. Question? Oh, things made of earth or water naturally want to come to rest. So if the ball eventually came to rest, Aristotle would say it came to rest just because that's what it naturally wants to do. But what we now know is things come to rest because a force is exerted on them. If there was no friction and I rolled a ball and there was no air resistance or friction, that ball would continue to roll at the same speed in a straight line forever. Other thing he did is he looked at balls rolling down one plane and then up another plane. And what he noticed is that if I had a ball starting at some initial height and it rolled down one plane and then up another, it would always roll to the exact same height. And we'll see later this is because of something called conservation of energy. And it doesn't matter what the slope was, it would always tend to roll to the exact same height it started at. And then what he thought was, well, what happens if I didn't have a slope on the other end? How far would it have to roll to get to the same height? And the answer is, it would roll forever. The only reason things come to rest on the earth is because forces such as friction or air resistance are impeding their motion. Now, we don't experience this every day because we live in a world of friction. We live in a world of air resistance. But in space, right, you've got these asteroids and meteors. Something started them moving. But once they start moving, their natural tendency is to keep moving in a straight line at a constant speed forever. Now, if they come close to another star or something like that, the force of gravity could cause them to turn. But if I have an object in space which is moving and it's far from any other sources of gravity, it'll move in a straight line at a constant speed forever. So Galileo was the very first person to really start to question Aristotle. Galileo was the first person to come up with this concept of inertia. So let me go to here for a second. So what Galileo discovered was this concept of inertia, and I'll define it in a second. But inertia is just a tendency of objects to keep doing whatever they were doing. If the object is at rest, the natural tendency is to stay at rest. But what he discovered was that if an object is moving, the natural tendency is not to come to rest, it's to keep moving in a straight line at a constant speed forever. So what he was the first person to realize is that a moving object does not need a force to keep it moving if there is no friction or air resistance or anything like that. So Galileo's concept of inertia, and I'm going to define this in a second, he said it's a property of matter that resists changes in motion, and it depends upon the object's mass. The more mass an object has, the more inertia it has, the more it's going to tend to keep doing whatever it was doing. So Galileo, the very first person to sort of introduce the concept of inertia. Now, Newton was the first person to sort of formalize this and then develop the mathematics to actually discover it. So we're going to be studying Newton's laws in the next few weeks. And Newton was really the very first person to sort of pull all of this together. Unfortunately, he was kind of an asshole. I mean, I'm not going to go into it, but he was not a very nice person. He was brilliant, 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 but he was kind of a jerk.
Can I ask a random question?
Of course, Eve.
So I just took philosophy, and I don't know how much philosophy and physics like intertwine, but wasn't Aristotle more of like a philosopher than like into physics?
Yes, he was sort of an all-around brilliant guy. He was a philosopher, he was a scientist.
Oh.
Now we look back and it seems like a lot of his ideas seem silly, like the idea that the heavier an object was, the faster it would fall. But keep in mind, this is 300 BC. This is, you know, more than 2,000 years ago. Even ideas that we had 100 years ago now we know are not correct. So 2,000 years ago, yeah. Does that help? Okay.
Yeah, thank you.
You're welcome. Let's go. Okay, Newton. Okay, so we'll start with that. So let's go to these lecture notes for a second. Aristotle basically lived around 350 BC. He taught that the periodic table basically consisted of 5 elements: earth, water, air, and fire, and then quintessence. Anything on earth made of earth or water, the natural motion was straight down. Anything on earth made of air or fire, the natural motion was straight up. Anything in space made of quintessence, the natural motion was circular. We believe that for about 2,000 years, until Galileo started actually doing experiments with balls rolling down inclined planes and things like that. But it was Newton who was the first person to sort of formalize everything. He published this famous treatise on sort of motion, and he was the first person to really start to develop physics as we know it. And if you ever go into some history, Newton was really quite fascinating. Like, he needed more advanced mathematics to sort of study a lot of the motion and stuff like that. So he invented calculus. I mean, it's pretty cool. Like, we didn't have the math at the time, so he invented the math. Pretty amazing. Okay, so unfortunately, I can't do these demos, but I can sort of show you them as a video. Anytime you're doing inertia, you always sort of have to do the tablecloth trick of pulling a tablecloth out. So let me just stop this share for a second. And then I want to do a new share. Course module. And let me go to, okay. So I want to just show you a few quick videos. This is Paul Hewitt. He is the author of the textbook. And I just want to show you a couple videos about inertia.
So what's the force keeping it going? No force. We don't know why it keeps going. But we call that ignorance inertia. Get the idea? Nobody knows why it keeps going. We just know that it does. And so we call that inertia.
So let me just touch on that for a second. I'm going to do this in the lecture notes, but we do not know why.
The foundation of all science and technology is mathematics.
Sorry.
One of the most important branches of mathematics.
Go back to that. We do not know why in our universe, objects with mass want to continue doing what they're doing. Once an object starts moving and it has mass, its tendency is to keep moving in a straight line at a constant speed forever. We know so much. Physicists think they know what happened something like 10 to the minus 30 seconds after the Big Bang. We can trace sort of the history of the universe, but we don't really know why objects with mass have this property called inertia, where they want to keep doing whatever they were doing. Okay, here is the old tablecloth trick.
And what do we have down here again? We have some plates, no staples, no Velcro, the tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What I want you to do is they say, hey, what are you learning at the university? Say, I'll tell you what I've been learning at the university. Okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Hey, how about that?
Now, if you do this at home, let me warn you that you need to have a tablecloth that doesn't have any kind of seam or something at the end. My very first year of teaching, I think it was my first or second lecture, I had this set up. I had a tablecloth that had this little seam at the end, and I was like, I'm gonna put a couple glasses on it. I pulled it, the seam caught the glasses, knocked it over, the glass broke. It was a funny way to start the class, and students remembered it. But so if you're gonna do this at home, make sure you do not have a tablecloth that has a little seam at the end. And let me get that out of the way. Okay, so just one more. How do you use inertia every day? So I had a question like, how do you use inertia in the bathroom? Well, everything with mass has inertia, which means it has a tendency to stay at rest if it's at rest, or to stay moving if it's already moving. So if you are getting, let's say, some toilet paper, you do not have to brace the toilet paper with one hand and rip it off. The toilet paper roll has inertia, and if I pull it quick enough, because of the inertia, the toilet paper roll tends to stay at rest, so I can rip the paper.
You go to the store, you're getting some groceries at the store. You got the baggies, huh? You got the baggies all set, and you got all your bananas right here. You're gonna get the baggie. Do you have to put all the bananas down? Put one hand on top of the baggie thing and then pull the other one. Do you have to do that? No, you don't do that. You keep the bananas in one hand, you grab a baggie, you go, you snap it. And when you snap it, what happens? The roll of bag has so much inertia, stays right there, doesn't it? And boom, it'll snap away from you. Huh? How about when you're reading your book and you're on the toilet? Huh? What happens? You're on the toilet, you're reading a book like this. Do you have to stop when you're all through? Put this down, hold the top of the toilet paper, and tear to the bottom piece? You have to do that? You don't have to do that. You can keep reading the book, reach over, and snap down quick. And you rely on the inertia to hold it still. Is that true?
Stop that. Okay, let me just pause and open it up for any questions before we jump into inertia and looking at this in a bit more detail.
Without further ado, Professor Lewin.
Oh. I gotta get used to the fact that these YouTube videos keep playing. Okay, then let's go back to some lecture notes. So one, if you were to see an object suddenly start to move, you would most likely assume it moved because something exerted a force on it. We know basically from common sense that objects at rest, where's my pen? Sorry, I'm having a little technical difficulties. Okay, we know that basically from common sense, an object at rest is going to remain at rest unless some kind of force acts on it. Now, this is something that both Aristotle and Galileo would agree on, and obviously Newton. Where they wouldn't agree is Aristotle believed that a moving object would naturally come to rest on the Earth's surface if it was made of earth or water. What we now know is that a moving object doesn't naturally tend to come to rest, it naturally tends to keep moving. So same thing, one, let's say I threw an object. I don't know why I just have this easy button. If the object's at rest, its natural tendency is to stay at rest. But if I throw it, I'm exerting a force on it, causing it, we'll see it accelerate and start moving. Once though I let it go, my force of my hand is no longer being exerted, right? My hand's only exerting a force when it's in contact with the object. Once I let it go, the object keeps moving. Is there a force being exerted on it from my hand once I let it go? And the answer is no. The object keeps moving because of this thing called inertia. And inertia is basically the tendency of an object to resist changes in motion. Changes in motion means if it's at rest, changes in motion means it's no longer at rest. Or if it's moving, anytime I change the speed or change the direction would be a change in motion. So what we know is objects tend to remain either at rest or moving in a straight line at a constant speed. So this goes against what Aristotle taught. He taught that objects would naturally go to their resting place, either on the earth or straight up, depending on what they're made of. What we now know is that that's not true. An object tends to either stay at rest if it's already at rest, but if it's moving, the natural tendency is to keep moving in a straight line at a constant speed forever. Now, what does inertia depend upon? So inertia depends upon mass. And you kind of know this from everyday experience, right? If I'm trying to move an object, the heavier the object is, the harder it's going to be to move. And that's because the more mass an object has, the more inertia. So if I think about it, if I have more mass, I have more inertia. And if I have more inertia, I have more resistance to changing my motion. Now, again, the interesting thing is we've decided to call this property inertia, but ultimately at a very fundamental level, we don't know why objects with mass have this natural tendency to keep doing what they're doing. So physicists, super duper duper smart, we know an amazing amount of things, but ultimately we don't really know why objects that have mass have this natural tendency. You can imagine maybe there's another universe where objects do tend to naturally come to rest. But in our universe, objects with mass tend to keep doing what they're doing. If they're at rest, they tend to stay at rest. If they're moving, they tend to keep moving in a straight line at a constant speed. So the more inertia something has, the harder it is to start the object moving or to stop it from moving if it's already moving. And you kind of use this every day. And in fact, I used this the other day when I was having French fries, and I had a little bit of ketchup stuck at the end of the bottle, right? So you have a little bit of ketchup. What do you do to try and get that last little bit of ketchup in? You do one of these things. Why? Well, let's say this is a ketchup bottle. Ketchup bottle's at rest, the ketchup's at rest, the natural tendency is to stay at rest. But then I exert a force downward, causing the ketchup bottle to move downward, the ketchup to move downward. Then if I suddenly stop the bottle, the natural tendency of the ketchup is to keep moving in a straight line at a constant speed until something exerts a force on it. And that's going to be sort of a little bit of the friction between the ketchup and the bottle. But anytime you're doing one of these things to try and get that last little bit of ketchup or something out of the bottle, you're using the concept of inertia. I get the ketchup in the bottle moving, and then I stop the bottle with my hand, but the natural tendency of the ketchup is to keep moving. And this is exactly why you need a seatbelt, right? Let's say you're moving 50 miles an hour. You're with the car, you have mass, the car has mass, the natural tendency is to keep moving in a straight line at a constant speed. Now suddenly you hit something. Whatever you hit is a force on the car to cause the car to stop moving. But until something exerts a force on you, your natural tendency is to keep moving in a straight line at a constant speed until something exerts a force on you. What you don't want that object to be is the windshield. And so the seat belt is there to sort of stop you from continuing to move forward if you brake suddenly. Okay. So I want to show you a couple videos. It's interesting. So everything with mass has inertia. Everything with inertia tends to either stay at rest or moving in a straight line at a constant speed, including your blood. So let's say that you are a pilot flying a jet and you're flying maybe 500 or 600 miles an hour. You suddenly take a quick turn. Your blood has mass, which means the natural tendency of your blood is to keep moving in a straight line at a constant speed. But if the plane suddenly quickly accelerates, what can happen is your blood will actually start to drain from your brain because its tendency is to keep moving in a straight line at a constant speed while the plane takes a turn. If you take a turn fast enough, you can actually undergo what's called G-lock, which stands for gravitationally induced loss of consciousness. And fighter pilots actually have to train for this. So if you take a turn fast enough, you can have the blood, since it has a tendency to keep moving in a straight line at a constant speed, actually drain from your head. So let me show you a couple videos which are pretty cool. Let me share. Share screen. Whoop. I want to share that. Move this out of the way. Centrifuge. Okay, so one, let me just show you what these pilots are in. So this is called a centrifuge. And we're going to see this next chapter, but anytime you are moving in a circular path, you're accelerating, even if your speed isn't changing because your direction is changing. So what these pilots go in, it's called a centrifuge. And they basically just get into this contraption and it just starts spinning faster and faster and faster. As it's spinning faster and faster, the acceleration increases. And once the acceleration gets to a certain amount, you'll see a little thing in the corner here with G's. We're going to get to this next chapter, but the acceleration due to gravity, we give the symbol G. And I know we haven't had acceleration yet, but when you see 3 G's, that means 3 times the acceleration due to gravity. 4 G's, 4 times the acceleration due to gravity. So they have to train for this because you don't want to pass out if you're, let's say, in some kind of fight with other jets, if you have to take a turn too fast. So let me just show you a couple of these. It's pretty interesting.
Are you ready?
Yes, yes, sir. I'm ready.
Ready. 3, 2, 1, engage.
So it's starting to spin faster, or right now it's just at 1 G.
How you doing?
If you lose all the green, tell me now and start that lower body straight, okay?
Okay.
Squeeze those legs nice and tight. 1, 2, 3.
5 G's,
Looking real good. Squeeze everything nice and tight.
6 G's. Oh,
Not yet, not yet. It's only 2 G's. It's only 2 G's.
You should feel like you're going straight up in the air at this point.
That's 4 G right there. You're doing good.
3, 2, 1, engage. Back on the stick. On top. On top, breathe. You're on top, breathe. You're on top, breathe.
Okay, big breath. Walk out the road.
You're on top, breathe.
Go.
On top, breathe. 1, 2, 3.
1, 2, 3. Go to your breath.
1, 2, 3. 1, 2, 3. 1, 2, 3.
All right?
Go. Legs tight. Foot tight. Breathe.
1, 2, 3.
1, 2. Well, okay. Stay tight. Stay tight. Stay tight. Stay tight. Hello? Are you with me? You coming back around? Hello? How you doing?
What?
Hello, Will.
Hello.
Will, sit up.
I'm up.
Sit up.
I'm up.
You're up. Put your head up.
It is up.
Put your head up.
Oh,
Do you know what happened?
yeah.
You ain't lost.
Yeah.
Happened.
I'm taking out you are.
All right.
Okay. You all right? You feel nauseated? Yeah, a little bit. I'm gonna vomit. Okay, get the bag.
I think there's one other one where they had some that's fun. Let me just want to show you one. When you pass out, your body starts to a lot of time do these weird little jerky motions. Oh, okay, let me stop that. Share. Now, obviously the military can't have its pilots passing out whenever they take a really, really sharp turn. One, they train for it, but even if you train for it, it's still a strong possibility. So they're really, really smart. They actually have these suits now that are connected to the plane. And when this plane takes a sharp acceleration, the suits can sense that. And what it does, it's almost like when you take your blood pressure, it starts, you have that sleeve that you put around your arm. What they do is the suit basically inflates, exerts a force that will force the blood up into your brain. And so they have ways of sort of counteracting that. But very interesting. So the reason this happens, again, anything with mass has a tendency to keep moving in a straight line at a constant speed if it's already moving. If you take a quick turn, the natural tendency of the blood in your head is to keep moving in the same direction it was. And because of that, the blood pressure in the brain can drop and you can have people pass out. Kind of interesting. Okay, enough of that fun. Let's go back to the notes. Okay, so again, let me just emphasize, we don't know why objects with mass have inertia. Inertia is just a name that we as physicists have given to the tendency of objects to keep doing whatever they were doing. But ultimately, we don't know why objects with mass have inertia. So putting it all together, Newton's first law, there's different versions of it. The one that I like is, an object at rest tends to stay at rest. An object in motion tends to stay in motion in a straight line at a constant speed unless acted upon by an unbalanced force. And I'm going to get to this in a second, but unbalanced force means the sum of all forces is not zero. If the sum of forces equals zero, we call that a balanced force. So we're going to talk about this more in the next couple chapters, but if I, let's just say, had a box and I had two forces pulling on it in opposite directions, and those forces were equal. We're going to get to this in a second, but we measure forces in what's called newtons. So if I had two 10 Newton forces on opposite sides of an object, those two forces would balance out. We would call that a balanced force. However, so this would be a balanced force. However, if one of these forces were bigger, so let's say I had a 20 Newton force on one side and a 10 Newton force on the other side. Now I have more force on one side than the other. I have an unbalanced force, and that object would then either start moving if it was at rest, or it could speed up or slow down if it was already moving. So if all the forces on an object add to zero, then that object is either going to stay at rest if it's already at rest, or it's going to start to change its motion if it's moving. It'll either speed up, slow down, or possibly change direction. So let me just show you the way Hewitt puts Newton's first law. So another way of saying that is, every object continues in a state of rest or of uniform speed in a straight line unless acted upon by a non-zero net force. It says exactly the same thing. If it's at rest, tendencies to stay at rest. If it's moving, the tendencies to keep moving in a straight line at a constant speed until some unbalanced forces act on it. Okay. So let me pull up a question I want to ask you. So one, a headrest in a car, a lot of people think that's a comfort feature. It's not actually a comfort feature, it's an important safety feature. So in terms of Newton's first law, which we sometimes call the law of inertia, how does a car headrest help guard against whiplash in a rear end collision? So, you know, you're at the light, you're at a stoplight. You're just sitting there minding your own business, checking out people. Suddenly somebody's not paying attention, they rear end you from behind. The car headrest will actually help in terms of safety because of Newton's first law. Why is that? Well, if I'm at rest, the car's at rest, I have mass, the car has mass, our tendency is to stay at rest unless something exerts a force on us. Well, let's say you get rear-ended. Somebody hits the car. That is exerting a force on the car to cause the car to start moving. Well, the seat, if the seat didn't have a headrest, what would happen is the seat would cause the bottom part of your body to move. But if there's nothing exerting a force on your head's natural tendency is to stay at rest. So it's almost like one of those cartoons where the body moves and the head is way back here, but to a lesser extent. So what a headrest does is it moves your entire body forward at the same time. If the headrest wasn't there, your body, your head tends to stay at rest because of inertia. If the car gets rear-ended, your body is going to lurch forward because of the seat. But if you didn't have a headrest, then nothing would be causing your head to move forward until your neck stretched enough that it exerted a force on your head. So a car headrest is actually a safety feature, which basically moves your head forward at the same time as your body is moved forward. Let me pause. Does that make sense to people? So something has to exert a force to move your head forward. If you didn't have a headrest, the seat would cause your body to move forward while your head remained behind. So what a car headrest does is it moves your head forward at the same time as your body. Okay, I want to ask you a question here. Think about. Question 2 says, when the bullet fired into the spiral tube emerges, which path will it follow? So let's say, you know, I've got a gun shooting some sort of bullet. I've got this spiral here. And the question is, once it gets to this point here, which path is it going to follow? Path A, path B, or path C? I'm just going to pause 30 seconds, let you think about this. If you want to volunteer an answer, throw it in chat or unmute yourself.
Maybe A.
Sorry, I didn't hear that.
Maybe A.
Maybe A. It's a good guess, and that seems like what it would do. But, nope, let's see a chat here. Chat. B. So, rather than give you the answer, let me see if I can show you this video. Pause. Let's do a new share. Okay, so this is basically the same setup. Is we've got a ball here, you've got sort of a little track here, but then once it gets here, we want to know what happens. Which path is it going to take? Let's play that one more time.
B.
Woo, doosh. So if this tube wasn't here, the gun is exerting a force on the ball, causing it to start to move. If there was no tube there, no other forces, the ball would continue to move in a straight line at a constant speed. But the tube is exerting a force on the ball. Come on, where's my... The tube is exerting a force on the ball, causing it to change direction. But once I get to this point here, now the tube is no longer exerting a force on the ball. The natural tendency of the ball is to move in a straight line at a constant speed. So I forget what it is, but you know, there was the old weapon where they would take rocks in a little thing and swing it and then let it go, right? Once you let it go, the rock doesn't continue to sort of move in a circle. Once you let it go, it's going to move in a straight line at a constant speed forever. Well, it's not exactly true because of gravity. We'll see gravity is going to cause the object to tend to accelerate towards the Earth. But if I threw something in space, you know, I'm twirling it and then I let it go. Once I let it go, that thing is just going to continue moving in a straight line at a constant speed, basically until something else exerts a force on it. Okay, I think I'll do a couple more things. So does that make sense in terms of that clicker question? So the answer was B, because once it leaves the spiral tube, if there's no other forces acting on it, it's going to continue to move in a straight line at a constant speed. Okay, let's go back to this. So one, let's just talk about what is a force. You guys are probably familiar. Force can just be considered it won't let me write. Draw. So a force is just a push or pull, right? If you wanted to exert a force on me for some reason, maybe you didn't like the way I graded your quiz or something, what would you do? You'd grab me, you push me, you pull me, something like that. So the very simplest definition of a force is a push or pull. It's exerted by one object on another. We're going to study gravity and electricity and magnetism. So there's different ways of exerting forces. Force of gravity, any object with mass will exert a force on another object, even if they're not touching. We have electrical forces, magnetic forces, or simply muscular effort. So if I want to exert a force on an object, generally I'm going to push the object or pull it. We as physicists measure force in something called newtons. Why do you think it's called newtons? Because Newton was basically the first person to really study forces and formalize it. In physics, we tend to name units after the scientist who first studied it. So we name force newtons. Once we study energy, we'll see energy is measured in joules. I'm hoping that I inspire some of you to become great physicists. You make a great discovery and you name a unit the Joe. It's just a dream. Anyway, just so you know, in terms of thinking about it, we measure force in our units that we use in the United States in pounds. So when you step on a scale, what you're really measuring, and we'll get to this in a couple chapters, is not your mass, but your weight, which is the force of gravity on you. And technically, you'll see that you weigh a different amount, let's say in Colorado, than you do in Santa Cruz, because the farther you are from the center of the Earth, the less gravity pulls on you. So if you had a sensitive enough scale, you would find that your weight at sea level is different than your weight on top of a mountain or your weight in Colorado. It's kind of interesting. Well, a Newton, just so you know, 1 Newton, it's a good little thing to know, is about a quarter pound of force. Quarter pound, whoa, what's going on here? Technical difficulties. Draw. Erase. So 1 Newton's about a quarter pound of force. So you go to Burger King, you order a quarter pounder. The amount of force it takes to lift it up, pre-cook weight, is about a Newton of force. So the last thing I'll say to sort of end here is when more than one force acts on an object, what we have to consider is what's called the net force. And this is the sum of all forces. And a force is something called a vector, which means in order to describe it completely, I need to know the direction the force acts. So let me just sort of summarize everything and then see if there's any questions. And if not, we will sort of stop there. So one, just gave a quick little historical perspective. Talked about what Aristotle believed. He believed that there were basically 5 elements: earth, water, air, fire, and quintessence. Anything made of earth and water, their natural motion was to move down towards the earth. Anything made of air and fire, natural tendency was to move up. And then anything made of quintessence, the natural motion was circular. He believed that objects naturally tended to come to rest at their natural resting spot. Galileo was the first person to really go against this, and he came up with the concept of inertia, which says that objects with mass tend to continue doing what they were doing. And then Newton was the first person to really formalize all of this. Newton came up with the concept of inertia, which just said that objects tend to keep doing whatever they were doing. If they're at rest, they tend to stay at rest. If they're moving, they tend to keep moving in a straight line at a constant speed forever. And what we know is that inertia depends on mass. The more mass, the more inertia, the more something resists changing its motion. And then Newton's first law just says that object at rest tends to stay at rest. An object in motion tends to stay in motion in a straight line at a constant speed unless an unbalanced force acts on it, which means the sum of the forces is not 0. And a force is really just a push or pull. And then in physics, we measure force in a unit called newtons, and a newton is about a quarter pound of force. And I think that's where I want to pause for today. What I'm going to do is I will upload this video to YouTube, like I said, and I'll put a link to it. And then, yeah, we're going to continue with that on Thursday. So let me pause, open it up to any questions you have about any aspect of Physics 10 or about this particular topic, Newton's first law. No? Well, thank you so much for joining me. It's nice to see a few faces. And yeah, please let me know if you have any questions. And if not, I'll see you on Thursday.
Thanks, Joe.
All right. Thank you so much, everyone. Have a wonderful day. I will talk to you all later.
Thanks.
Bye. Bye-bye.